Hello and welcome back to ST118 Statistics and Applications, Session 5. In this video, I'd like to share with you another two beautiful tests. Very useful. And let me just put them under distribution fit tests, right? So is to test whether having taken sample values and measurements, whether the population's distribution, that means the shape, right, of the histogram if drawn of the population matches what we expect, fits certain prescribed distribution. So let me just maybe just fan out the two tests. All right. So first is perhaps you have heard of it, the goodness of fit or chi-square goodness of fit. Chi-square goodness of fit more because it's using the chi-square distribution. So you might have heard of it as chi-square goodness of fit test or just goodness of fit test. And the other one is the independence test. Independence test. Test whether two populations are independent of each other. They statistically don't behave in a way that would match the independence criteria. So independence criteria, we discuss it in the probability video to mean that if I give you an information about population 2, the population 1 measurements doesn't get affected at all. That means if it's going to be a high value, it will be high value. If it's going to be low value, it's low value. It doesn't get affected at all. That means they are independent. And likewise for population 2, if I were to give you information about population 1. So example, hey, population 2, the values are all very high. Whether it is measuring height or weight or test scores or performance or productivity, right? And then if population 1, perhaps the employees of a competitor, and having heard that, they start to work harder, right? The boss reacts and makes sure that his employees are working even better, higher, right, value than population 2. Then it is no longer independent. So that's basically the idea. But I don't want to get into the detailed statistical mathematics about the definition of independence, but you can feel that this notion of independence, that means no influence of each other, so that the measurements start to change, right? Is a very commonly encountered situation, although we cannot directly see independence, but over time, gathering the behavior and activities done in reaction to certain stimulus or events, we can start to see some independence. But having a certain reaction doesn't necessarily fit the statistical definition of independence, right? So that's why we need to check, are the two populations independent of each other? So that's a very useful test because it's a very important notion in statistics. Many theories and procedures and methods, they become mathematically a lot simpler when we assume independence, right? Although it's kind of the contrary, in my opinion, in real life. Many things are not completely right, air-gapped. Many measurements, many information flow, many conversations, activities, numerical or non-numerical data, they are not independent from one another. Although the influence might be very little, so little that we can just kind of ignore it and treat them as independent, not influencing one another. And just quick example, right? So we are in Singapore. Is a huge forest fire in Brazil, Amazon forest or whatever, is that going to affect our lives? Well, one could say, well, it's so far away, right? Okay, so no influence, independent. But over time, right, the huge forest fires is going to, burn away the lung for the earth, right? So the trees are lesser, the oxygen production is lesser. Then eventually, it's like the butterfly effect, right? So eventually we will still be affected. So it's that kind of lack of complete independence, right? But oftentimes the influence is so minute right now, right, instantaneously, that we would say, okay, good, that fits our experimental assumption. That's good enough for us for now. So we need this test to I don't want to use the word proof because we're not doing science here. We are just trying to find data and analytics to give support to our conclusion, right? So if we manage to reject the hypothesis, then we'll say, oh, the two populations are not independent, right? We'll see how using an example, right? So why do I put both of them here? If you're looking at these words the first time, they might look very independent. They might look very unrelated, right? So, okay. So, let me just put down some characteristics. Okay, so this uses, obviously, chi-square. I'm just going to write the Greek letter since no, it's a lot easier just to write the Greek letter. And this also uses chi-square. Okay. So, interesting, right? So they use the same chi-square, but doesn't mean anything, right? Because many different natured tests, hypothesis tests, in our earlier discussions, they also end up using T, using F, right? So what's the big deal here? Well, here we have one sample because the goal is to, right, check if this population fits a prescribed standard distribution, I need to say. Standard distribution means they are mathematically derived. They are created, or I would created by mathematicians, but like conjured up by magicians, right? So they're like, ring, the formula comes out. Normal distribution is one such standard distribution, right? And standard normal, which is a normal distribution with a mean of 0, standard deviation of 1, that is also a standard distribution. All T distributions, all chi-square, all F distributions, all gamma distributions, beta distributions, Weibull distributions, you can name it, right? Just Wikipedia, you see like 30 over the kinds of distributions. They are all described by mathematical formula. Now, just look at the formula, what is called a PDF, probability density function, that describes the shape, or rather the distribution of the entire population. And of course, being a mathematical construct, we can describe the entire infinite number of measurements in the population, right? Because it's a completely virtual object created in the mathematical world. Compared with the independence test. So this test, it involves two samples, right? Samples. Because we are trying to sample one sample set from population 1, another sample set from population 2, and see if, not whether their distributions match or not, because we have a Kolmogorov-Smirnov test that we discussed earlier to test for normality. But the two sample version for Kolmogorov-Smirnov test is to see if the two populations have the same distribution. Same means they are the same. That means they are the same, which is equal to normal, or they are the same, which is equal to uniform, right? They are the same, which is equal to chi-square. It doesn't matter. So long as they are the same, then Kolmogorov-Smirnov two-sample test will review so. This test, however, involves two samples, but not to test whether the two population distributions are the same or not. Rather, the goal, right, is to test if the two population, the two populations are a population-wise as a data cloud, as two blocks of data clouds, right, are independent, right? Not point by point, like one point associates with another point like that, but as data clouds. Are they like totally don't react? Think of them as two balls of chemical compounds, right? When you put them in proximity, do they react? Do they react? Do they, fuse together to become something else? That means they are not independent, right? So that kind of thing. So are they not influencing each other in the measurements? That's what we are trying to test for, right? So a rather important tool, don't you think? Because this effect is not so visible, so readily measurable, and we have to deduce this aspect of the population cloud based on the two small sample sets that we get. Hopefully bigger sample sets. I'm just trying to say that the two samples that we extract from the two population clouds, they are small, right? How do you conclude about the whole population being independent of the other? So that's, but chi-square independence test is designed to do this. All right, so the two goals are kind of the same, kind of different. Why? Well, they look different the way I put it here, but the way this is done, right, the independence test, is like trying to induce or create an independent distribution. That's the way I look at it, right? The way I try to, if you look at the calculation steps, they are precisely doing that. They assume that the two populations are independent, and because of that assumption, right, the hypothesis first, right? Because of that assumption, it would result in an induced distribution due to the independence assumption. So I'll just call it the independence distribution. Right? So assuming they are independent, the two populations are independent, it will induce a independence distribution, which would then allow us to do calculations. So we say, are these two populations matching the induced independence distribution's shape? If the samples reveal so, that means there's a goodness of fit of the two samples. That means the two samples are treated as one pair of samples. Okay, so one pair of samples, do they match the induced independence distribution? Remember, distribution is population, right? If so, then yes, the two populations are independent, right? So otherwise, not. So we'll talk more about that. And because of that calculation procedure, matching very much like the goodness of it, this is like a two-dimensional version of goodness of it. So think of it as uh, a 2D, two-dimensional version of goodness of it. Once you can accept this, of course, I need to discuss this more, right? Once you can accept this, then you see why they are very related. So they are basically using the error calculation again to see if the error accumulated is very huge. And the goodness of it is for one dimensional, one population test, and then the independence test is to have two populations, right? So it's two-dimensional and test specifically for this aspect of the interaction between the two populations, which is independence. Okay, so let's go on with our discussion of not chi-square, but goodness of fit. Test by using an example, right? So our goal is to test whether, right, the sample comes from normal distribution, and for that matter, it can be anything. All right, so test if sample comes from normal distribution with a mean of 100, standard deviation of 10. Our guess, our like hypothesized population mean, hypothesized, what do you call that? Standard deviation. All right, so, but we are not trying to test for the mean alone, the standard deviation alone. We are testing for the normal shape, right? So if we gather some samples, can we conclude that the population is following this? Okay, so our sample, let's say it is the set 85, 92, 102, 108, 113, right? Of course, they can be all jumbled up. Okay. So what do we want to do with this? First thing first, we can tabulate them. So X is this. We need to cut up, right? Cut up the normal bell curve into bins, right? So it's probably good to look at a small little diagram, not a big one, because we all know what a bell curve looks like. But I think it's helpful to have this little chart here just to show us. So because bell curve goes from minus infinity to infinity, right? It's a good idea to, collect the tails into one of the bins. So like this. So 3 points, we get 4 bins, right? And 1, 2, 3, 4, right? So you can then understand why I would say the bins, right? So the categories, the intervals would be less than 90, 90 to 100, 100 to 110, greater than 110. For continuous data assumption here, continuous data, right? We are using it on the real axis. Equal sign is not so critical. So whether you put greater, equal, simply because of one observation that on the continuous distribution, the probability of x being equal to any specific one number, not an interval, just one number, is the area. So the area from 100 to 100, the area from 90 to 90 is 0, right? So probability being equal to the area, we know that the probability of x equal to any number is 0. So it doesn't matter whether you include the equal sign or not. Doesn't matter in the sense that it's not consequential in the calculation. Next, what we want to do is to look at the count of data, right? So looking at the count, one sample falls below, and we have 92, 102, right? So we can quickly do that, and of course using program codes, this will be done very quickly. Next, we want to calculate from the assumed, right, distribution, this given one, right? What is the actual probability of going below, right? I just alternate the colors. to show the bins more clearly. All right. So calculate the probabilities. And okay, so we are going to basically show the probabilities, the expected probabilities. So the expected probabilities of bins, right, within the intervals. We will use, of course, normal distributions, CTF, cumulative distribution function, and you can do that readily with Excel, R, or Python. 1587 0.3413, and then same here because there's a symmetry about the mean 100, the assumed mean 100. 1587 also. Okay, so it's symmetrical and not surprising, right? Then our goal is not expected probabilities because this is just based on the picture here, right? Our goal is the expected count. That means if the samples came from this beautiful, right, normal distribution of this mean and this standard deviation. And by the way, this mean and this standard deviation is part of the description of the normal distribution. In other words, the whole thing is one. So we're not looking at 1, 2, 3 like that. We're looking at one thing only. Yeah. So we're saying, is our real life population matching this thing, this standard distribution? Right? Or doesn't deviate too much. There may be noise, but the noise is not so intense that statistically it is not considered a normal anymore, right? So this normal anymore. Also, if we fail to match the sample's population to this normal, it could match another normal. In other words, if we fail to match this x to this normal curve, it may match another normal with a mean of 200, standard deviation of 10, right? So we can keep going. So we look at this as one. Then we calculate by using the sample, the sample size times the expected probability. So our sample size n equals to 5. So n equals to 5. 1, 2, 3, 4, 5. Yeah. So 5 times this, I get 0.7934. And of course, we will get a lot of decimal places simply because the probabilities will have decimal places due to the standard distributions mathematical formula, right? So it's not surprising to have fractional, very, very fractionalized. Make sure I don't copy the wrong number when I narrate my thoughts. Okay, so the expected frequencies are going to be just that, fractional. No problem at all. Just leave it there, right? So because we're going to calculate the errors. This sample count is going to be very integer because we literally count the occurrences. This expected count is very theoretical, right? Based on the expected probabilities from the given distribution. Okay. Next, we will calculate the chi-square term values, which is observed. So this is observed, and this is our expected. Right. So typically, if you Google around, all the literature, even textbooks, right, will use O for observed, E for expected. I mean, try not to change it to S or SC, sample count or whatnot. So more because the formula is very international, right? So the formula is going to be calculating the relative squared differences in frequencies. Let me say again, the relative because there is an over E, over the expected. So why over the expected, not over the count? Because expected is what we are kind of assuming, right? Remember, throughout our hypothesis calculations, we assume H0 is true. Oops. I'm asking the question you're asking. So what is the hypothesis, right? We haven't written down, but not difficult. So we start with the standard hypothesis. H naught is population follows normal distribution with a mean of 100, standard deviation of 10. Population does not follow the given distribution. Very simple, right? So the way it goes is to calculate the squared difference from the expected. So when we hold this to be true, we need to find the relative to the H naught, right? Relative to this distribution. So hence divide by E, not by O. And the numerator, we square it because we are trying to find the cumulative errors or the deviations from the expected frequency, whether you in this case exceed or in this case you kind of went below, right? No, sorry, I'm comparing this one. So this one exceeds by a little bit. This one is insufficient. Okay, so there will be ups and downs because obviously real life measured numbers cannot be fitting a mathematical perfect ideal object exactly all the time, correct? Not everywhere. Cannot be. So there will be some deviations, called errors, and by squaring, we are trying to obtain in a very mathematically nice way the only the positive values. All right. So of course we can take the absolute values, but this was developed many years, decades ago, right? And at that time there was no computer or whatnot, so squaring is always a more preferred way to get rid of negative sign. So the errors, right, the errors in the frequencies between the observed and expected relative to the expected, in other words, relative frequency of errors in terms of the counts, right, fractional values included. What will they be term for term? 0.0539. So let me write that down. 0.0539 and 0.2926. They are fractional. They are in other words, they are less than 1, but could be larger than 1 because of the square. If the error is larger, if the difference is larger than 1, then squaring will make it even larger. Then divide by E, it could end up that the whole ratio is a large number, possibly. But it all depends on the observation of the data and our assumption, right? If our assumption is a very wrong normal, like mean of 0, then obviously every term is going to be having a large error, which will make our final accumulated error, which is the chi-square test statistic itself, very large, and then into the rejection region. Okay, so final tally is that our chi-square test statistic is the chi-square symbol, right? So chi-square is the sum of all the I in the bins number of bins. So we have 1, 2, 3, 4. So 4 bins. Notice that n is 5. N is 5. This is what is used here. But number of bins, that's 4. And could be lesser if we choose to bunch them up. Also, you need to watch carefully, right? Number of bins. The error term here, so minus E squared over E for each of the K. So when we tabulate out as a table, it doesn't look so scary because we are doing the K equals to 1, 2, 3, 4 like that. So actually this is a very compact form. If you understand it, it's very compact and it tells you exactly this whole thing. But let's sum them up. And what do I get? I get, in our case, I get 0.4578 4508. Okay, so this is our chi-square for this example. And so we need to look up the table, right? This lives in the chi-square distribution. Chi-square requires degree of freedom, just like T distribution, F distribution. Degree of freedom is number of bins minus 1, all right? Number of bins minus 1 minus any, let me put this square bracket, that means optionally minus any other estimates. Using sample. What do you mean by that? Well, in our example here, we did not use any estimates from our sample here. We did not. Why? We did not use any estimates for population. Right? Our population is N110. It's like we dreamt about this distribution. So we thought about it and hey, let's see if this sample is matching this. This 110 just somehow came up and it's the right choice. But of course, in real life, how do you know, right? How do you know this doesn't fit 98 and standard deviation 8.5 better? How do you know, right? How do you know it's such a nice number? Convenient, right? 110. But how do you know another close by number, maybe with some decimal places, wouldn't fit this even better, right? And then you would then be able to say that yeah, it is actually shape is normal, just that you are guessing the wrong mean and the wrong fatness standard deviation, right? So oftentimes in practice, we will use the sample like this, find the x bar, find the s, right? So when we do that, we will get x bar and s from the sample. When we use these two to replace the 100 and the 10, because obviously sample mean point estimates the mu, the appropriate mu if the population were to follow normal, right? And the sample standard deviation point estimates sigma. So if we use these two, then we get what we want, because no one can accuse us of saying, how convenient, they look so perfect. How do you know that these are the right numbers? Then we can say that, hey, we have justification. However, when you do that, you lose 2 more degrees of freedom. All right, so it'll be 4, because there are 4 bins, 4 minus 1. In our case, it is 3, right? So df equals to 4 minus 1 minus 0, so 3. We did not use. But if we were to use the sample, mean sample SD to replace the 100 and the 10, then clearly there will be decimal places. Then, of course, someone will say, you just try to put in some random digits in the decimal places to make it look scarier, more professional, is it? No, sorry, I didn't do that. Well, I'm using X bar and S, right? So you do that. However, when you do this, you lose 2 more degrees of freedom. So df3 becomes df1. Now, what's the big deal here? As you probably have gathered through my discussions in earlier videos, df is a bit like the fidelity. Most of the time it's related to sample size, right? So in this case, it's a little bit detached, although not totally unrelated to sample size. The bigger the samples, the more bins we would be feeling comfortable to create, right? Because number of bins is up to us. We can also bunch up everything as 1 bin or 2 bins, but you're just creating nonsense for yourself, right? So why do that? So we create an appropriate bins, and the appropriate number of bins also depends on how large your sample count, sample size is, right? Because if you have very little samples, you cannot be creating 10 bins. Some bins will be 0, right? And you're just asking for a problem, because you're asking for some of the bins to be 0 count and yet have non-zero expected frequencies, thereby creating more errors, finally rejecting the null hypothesis, right? So we're not going to do that. So we try to ensure that the bins are appropriate, like they are equal intervals or roughly equal in the bin size. You see, normal goes from minus infinity to infinity. So if you go by only the x-axis in equal x-axis intervals, then we have problem, right? So we want to also roughly look at the y-axis. That means the probabilities on top. We don't want to ensure that the segments all have equal probabilities. Then we also be in trouble. So it's kind of a little bit of an art, a little bit of a subjectivity there. But I hope you all will agree that this division seems very reasonable, right? Anyone would accept it as fair number of bins with the right intervals. So when we do this, then what happens? We only have 4 bins, and I mean with a smaller sample size and different standard deviation, we could end up having only 3 bins. So minusing 2, the bigger number of DF means the higher fidelity, the more resolution, like in a picture taken with higher resolution camera. So DF larger typically means more reliable outputs. When you have a penalty in DF, remember in the 2 population means test with unpaired samples, right? With small sample sizes, one way to deal with small sample size is to use the Welch-Satterthwaite formula to downgrade our DF. So our DF was calculated to be n minus 2, n1 plus n2, right? Minus 2. Using the Welch-Satterthwaite's formula, we're going to subtract some more, right? So we're going to n minus 2, let's say is 10. We're going to, after calculation, maybe become 6.72. So it's like a drop in our fidelity. We don't know the extreme values well anymore. Or we don't know the extreme values behavior, chances of occurring as well as we thought we know. So this is to give you a feel that this is a serious style, right? This is like saying, you know what, I'm going to penalize you for that. So when you have such situations, right, typically not only that we capture data for the purpose of the chi-square goodness of fit test, but we may also oversample, right? We may also have another sample set, perhaps that other sample set drawn from the same population could be a sample size of 5, right? Then that sample, which is not used here, is going to separately estimate X bar and S. Then you're not using this sample, right? So if you're drawing another sample completely separately from this sample, so this sample has no knowledge of your measurement of another sample drawn from the same population. So you're studying one population, but you're drawing 2 sample sets. One sample set is this, meant for chi-square use. The other sample set is to estimate X bar and S, so as to substitute into this hypothesis. If that's the case, then you minus 0, because you never touch this sample. You didn't downgrade the fed-in data's integrity, right? So you still maintain as free, right? Or whatever is the bin minus 1. Okay, so just so you understand. So it's a little bit of a carefulness there, tricky part there. So just so that you are using, especially when you have small number of bins, then a change of 1 in DF may cause the critical value and the critical value to shift a lot, and your conclusion may change. All right. Okay, so at this point, it's always good to have a diagram of the chi-square. Chi-square, again, very much like F distribution, starts from 0 and goes up, then goes towards infinity. So you cannot tell whether I'm drawing chi-square or F distribution, because chi-square and F, they are also related, right? So based on this, I obtained, well, what's my alpha? My alpha is 5%, right? And of course, this value is more like accumulation of errors. When the error is very huge, then the deviation from the assumed normal is very large, then basically it's no longer a normal distribution in the null hypothesis, right? So it is a right tail, well, on the distribution, it is a right tail. Okay, so it is a right tail test here, and our alpha is 5%. Okay, the critical value is doing a lookup. But you can use chi-square dot inverse in Excel or Q chi-square Q one tau to get the value, which is what 7.8147. So here the chi-square critical value is 7.8147, which is very large. And our Google pin is going to be here. I'm exaggerating the offset from 0 just to show that it is away from 0, but certainly not able to reject, right? So our p-value will be here. Rejection region is from here onwards towards infinity. So our p-value is from the starting from the test statistic all the way to the infinity, pointing to by the rejection region. So what's our p-value? Very large, 9296. So the p-value is 0.9296. And by now, you can already recite the conclusion, right? So for sake of completeness, we'll just write down, since p-value is 0.9296 and is not less than alpha, which is 0.05, we are unable to, right? So just say do not reject H naught and conclude that since we did not reject H naught, we look at H naught and say what it said in English. Well, it's already kind of in English. And conclude that population follows normal distribution, right, with mean 100. Well, I shouldn't be using mu. And standard deviation, I shouldn't be using sigma. Standard deviation equals to 10. Right, at 5% significance level. Okay, so basically that's it. Now, caution here, right? Caution here. Sample size 5 is too small, right? For chi-square results to be reliable. So in the small sample size case, to test normality, we want to use Shapiro-Wilk test, which is designed for normality test. Specifically for normality test, cannot be used for uniform and whatnot, right? And also, it is sharpened, is a sharpened tool for small sample size. It deals with small sample size very willingly and nicely. Its engine is trending up very well, right, with small sample size. So in this case, small sample size, and we're trying to test for normality, use some other tests like Shapiro-Wilk test, right? Then another point to note is that if you're not testing for normality, you're testing for uniform, for chi-square, for some other standard distributions, then no choice. You cannot use Shapiro. Then you have to increase your sample size. So because this outcome, we will have an outcome. We will have a total of the errors induced. But do you trust it or not? Right? That's the question. Right? So we want to touch reality more. And that is a rule that doesn't change. Right? It's like you cover up your eyes and then say, this place is so beautiful, this scene is so nice. Who will trust your outcome? Because you have not even sampled, right? You haven't even seen the scenery, and then you say this place is so nice, right? So that's exactly the case. Your sample size is 0. People look at you, your eyes are covered. How do you know the place is nice, right? So I don't trust your travel review anymore. So that's the same here. Also have a larger sample size. This is, of course, on top and overriding all the features and benefits and robust characteristics about robustness of non-parametric test and this test and that test. It is designed for small sample size. Things like that. They are true in the sense that they don't themselves create trouble just due to sample size, right? That's it. But small sample size just means small sample size. It's like a camera that functions very well with low resolution, right? Very, very small resolution, 320 by 240. We don't want this kind of camera anymore. So this camera functions very well. It takes pictures, right? The pictures are very pixelated when enlarged. And that by itself will always be there because the camera functions very well. It takes perfect 320 by 240 pixel pictures, right? Very low resolution pictures, but it functions perfectly. That's the kind of thing we are talking about, right? Yet nobody wants this camera. It is brand new. It is brand new. It is from branded manufacturer. It is very reliable. You can drop on the floor and it still functions, right? You can have all the robustness you want, but the resolution remains low. And we all know that this kind of camera, even brand new, robust, outdoor, outdoor proof, you can like go to rugged places and it doesn't break and all that. Waterproof, but we all know that the inherent problem is we need higher resolution, right? And that's not going to change with the robustness of the camera. So same thing here, the robustness of certain tests, right? The non-parametric nature that doesn't depend on assumptions, they don't change the fact that higher sample size still will be giving us more reliable, more trustable, right, more defensible outcomes, whether rejection or not rejection of the H naught. Next is that this goodness of fit test can be used for categorical data also. Okay, so example, 5 kinds of fruits. We want to test for popularity, perhaps in terms of favorite fruits, right? The assumption is that the 5 fruits, apple, banana, cherry, durian, E, any fruit that starts with E and E. Okay, papaya, that's it. Okay, so these 5 kinds of fruits, we, you know, interview people to seek their inputs. Maybe our sample size is 50 or 100, right? Then we start to do bins. We can do bins, right? And the bins are automatically the qualitative values, right? So apple, banana, cherry, and then papaya, right? So the 5 bins, and then we put in the counts, right? The people, they will say, yeah, that apple is my favorite, and then some will say cherry is my favorite. So we put in the counts, and then based on uniform distribution, we can carve out into 5 equal bins, and then we can calculate frequencies, expected frequencies, probabilities, expected frequencies, and then we can compute this. So you can see that this whole procedure can be repeated entirely, right, for categorical data, which is magnificent, right? So matching uniform distribution is a very perhaps boring question or exercise statistically, but that has tremendous meaning, right, in real life, because if it matches uniform distribution subject to some wriggling noise, then we say that, hey, you know what, it is shown, and with very good data analytics support, that the five fruits or the five sports or the five stocks, right, they are equally popular. I have data to support that, right? It's no longer just I think. So that's the power of this, of using goodness of fit, right? And so uh, remember the wide applicability of this goodness of fit test. Okay, parametric or not? This is interesting, right? So maybe we can put here that the chi-square goodness of fit test is somewhat parametric. somewhat somewhat non-parametric. Non-parametric. Why? It depends on whether we incur the loss of degree of freedom here or not. If we didn't, as in this example, we conjure up, right, the numbers, we dreamt about it. Our experience working on this, whatever is this situation, gives us this good feel, good estimate, right? But typically, even if you are very experienced in conducting tests, measurements, sports, whatever these data came from, your experience can't predict what is the right numbers right now. Yeah. So if you are testing a completely described population, like this case, then no penalty of degree of freedom, then it's a non-parametric test, because we're just doing the count. However, if we use samples to point estimate, we're beginning to assume, right, that the population number follows the X bar, example 95, right, or 96. And we also point estimate using the sample standard deviation. So we lost 2 degrees of freedom. Or if you use one of them, like you know that the mean due to manufacturing specification, right, it has to be 100. So you know that the population mean has to be 100. But you're not sure of this batch of production because it can be highly fluctuating. That's why causing a lot of defects, or very fine control, right? So the standard deviation is smaller. And you don't know which number is good to use. The engineering spec is 2. But the reason why you are investigating is obviously there's a lot of defects coming out. We are wondering what's happening, right? So that's why this number could have already drifted upwards. We don't know. And how up is upwards, you need to investigate. You cannot make an assumption, right or not? Yeah. So if you use the sample, this sample, to also extract one only, not X bar but S, or maybe you want to estimate X bar but not S, up to you. I'm just saying estimating S could be more frequently encountered in real life. So in that case, then you minus 1 here, or you get penalty of 1, not 2, right? Then in that case, you lost 1 degree of freedom, and that becomes no longer non-parametric. So long as you lose degree of freedom, then it becomes non-parametric. If it's non-parametric, then okay, fine, then we call it parametric, right? So in other words, there are occasions when this is non-parametric. Then there are real life occasions in practice. Most of the time we'll get penalty here, right? But then, as I said, even in real life, you can also segregate or dedicate another sample set unrelated to this one. You're just independently getting another sample measurements purely for the purpose of estimating X bar and S. And that sample doesn't participate in the chi-square test. Then it is like somehow you dreamt about the population fitting normal bracket 96, 5 square, right? So you somehow knew it, and that's thanks to a separate independent sample measure. So you need to, so in total, if your other sample has a sample size of 5, then in total you have a sample size or measurement budget of sample size 10, right? So that's why you did do more hard work, and you are not going to be penalized here. But probably you also merge it and then have a 10 sample size here participating, right? So then the bins can be larger, and then after subtracting, you still may be better off. I don't know. So up to you to try things out. So there's a big gray area zone, right? That's why we'll just leave it as that, somewhat non-parametric. Okay, and just to complete the story here, uh, the independence test is going to be parametric, non-parametric. Sorry. Okay, so comparatively speaking, the the distribution here is basically sort of like an independence distribution that is conjure up, right? Totally mathematically created. So no extraction of juice or information from the two sample sets. That's why it will be always non-parametric, in case you're curious. All right, so that is going to conclude our illustration of the example on goodness of fit test, right? And some of the areas to watch out for, and peculiarities and caution areas, right? And that's about it. Okay. Next, let me fly myself to the other side of the screen. I like to discuss via an example as usual, the independence test. Right? So very serious. Now the independence test is something we will need to run or we will need to conduct this test if we, number one, suspect that the populations are affected when we should not have such a case. So, for example, I can think of a tender process. Tender process means government or sometimes even large MNCs do that, right? So a government will say, I have this bridge to build. So who can build at the lowest cost? So of course, there'll be a lot of people interested in this, roughly $10 million project. But of course, there'll be background checks and all that. So let's say we have a short list, right? Down to two very strong competitors. So one bids 9.5 million. The other one bids 10.8 million. So if we just compare, we will take the 9.5 million, right? Because it's cheaper and they will agree to build everything. Then we want to know, are they independent or not? Are the codes given to the government, are they independently provided? So that would be one example to test for independence. It means the 9.5 million submission is totally from the vendor A's own calculation and own business intention. The 10.8 million offer by the other competitor, they are competitors, and it's completely derived from vendor B's calculations. They're not related. Okay. Why should government care whether they are independent or not? Well, if they are colluding, then this will be serious right now. Yeah, so both vendors might be penalized and even criminally charged for cheating the government, right? Because there may be a practice, a malpractice, that vendor A and B, they collude, they discuss backdoor and say, hey, you know what, vendor B, you let me win by allowing me to submit 9.5 million, right? And you submit a bit higher. Don't submit too high, because too high it may be not very easily detected. So you submit a bit higher than 10 million. Can okay? So they discuss, and there is a non-independent, right? That's collusion, right? So we just call it non-independence in statistics, very neutral, because in some occasions being non-independent is good, is what we expect, right? So not in this case. Notice I use the word non-independent. I don't say dependent. Because when you say dependent in statistics, you better describe the dependence behavior. To what extent do they depend? What's the function, the formula, right, to describe the intensity of the dependence? Is it 1 for 1, 1 for 2, what not? So is it immediate effect or whatnot? So all these become very complicated, and so it's better just to say non-independent, right? Non-independent. So as I was saying in the example, that if they collude, then it's non-independent, and government wants the submissions to be independent as possible, right? So in fact, if they're competitors and they are truly competing, because that's the whole idea of having a tender process to safeguard public money spending from the government. When the competing vendors want to bid successfully for the project, they better be the leanest, meanest, lowest offer price, right, to the government, and yet deliver all the quality and specifications that is needed to build the bridge. But when there's collusion, then there may be problem. So I gave the two numbers as 9.5 million, 10.8 million. But suppose everyone in this industry all know that the bridge is probably 10 million, right? What if they collude? And of course, vendor A can say, hey, you know what? You let me win. Telling vendor B. So you let me win. I'm going to offer the government 15 million. So please, you offer 16 or 18 million. Now you can understand what happens, right? So if there is lack of independence, then when submitted, government will shortlist everything. All vendors will submit very high offer prices, leading the government to think, hey, did I, unnecessarily underestimated the cost? So in the end, shortlist 15 million and 18 million. And after checking everything, and yet the government didn't check whether they are independent or not, then the project bridge is offered to vendor A. Now, what does vendor B get in order to purposely and knowingly offer something high in the price offer, knowing that it will not be able to get the job? Why would vendor B do that to help vendor A? Because 15 million, right? The cost is all everyone knows is about 10 million. And if you are very experienced, it may be even 9 or even 8 million, right? So there's profit. But on top of that, you get another 5 million free, right? So vendor A says, we split now, right? So we split, you get 2.5 million, I get 2.5 million. Is that okay? So vendor B, of course, will very happily oblige. It's like getting a profit of 2.5 million without doing anything, right? So why not? Okay, so vendor B. So if you didn't do independence test, then you wouldn't even know. But of course, independence test is not going to be 100%, right? So maybe by chance, but at least it is able to have another filter level just to weed out this possibility. Okay, so I hope through this discussion, this very narrated story, which is not rare at all, you can see why independence test is important. But even more than practical situation, there are a lot of procedures, calculations, tests, and all that require the populations involved to be independent. One quick example that I can recall is the linear regression or multiple linear regression. When the multiple populations that are or measurements or the random variables are involved, right, to calculate the model for the linear regression, those populations need to be mutually independent, right? So that's one big assumption. Is it true? We're just assuming, right? Okay. So if you haven't learned linear regression, don't worry, we have video to talk about that. And right now, let's focus on the example on test of independence. So let's begin by saying that we want a independence test example. Okay. Uh, Test whether uh, Group A and Group B. Okay, that means the grouping is independent of achieving success. Okay, that means maybe Group A is taught by a consultant and Group B is another consultant, right? So maybe Group A is a famous consultant, famous professor, and Group B is a uh, junior consultant, right? Very eager, energetic, right? And all the knowledge fresh and everything. Just that junior, maybe less practical experience. Okay, so does it matter? Does it affect the success and failure of the participating students, employees, and participants? Right, that's one. So the group A, group B is just generic here, but it could mean class A, class B. It could mean one university and another university. Right? Is it independent? Right. So is it true if that people attending NTU and NUS, right, will have non-independent success, right? Not we only know that attending one university is sort of like better than the other, right? So maybe there's rumor that coming to NTU study will have better career success after 3 years. Let's say we define all the points to measure what is the meaning of success, right? So all the boundaries and limitation, all the boundaries and lines are drawn very clearly, and they are measurable. All right. So okay, fine. So we can measure success and failure, right? So, and that's categorical outcome. We convert all the measurements, maybe multiple measurements of the individuals into success or failure, right? So two groupings, NTU and US. So there's maybe rumor saying those who attend NTU have better career success after 3 years, but maybe not so after uh, 1 year. So initially, it does look like attending NTU, right? Wow, takes time to find job or whatnot, right? And after 3 years, NTU graduates seems to be more successful than the other university, right? I probably shouldn't mention what the other university is. But is it true? That's rumor, right? Okay, so in order to quash this rumor, we set off to interview people and then put them. Of course, we'll interview NTU graduates and other university graduate, and then we'll measure, and put them under success, failure, right? So that would be the uh, premise, right? The sort of situation we are in to conduct this. If we fail to reject, right, then what happens? Then we will say that H naught, two populations are the two populations are independent. H1, two populations are not independent. So we keep to the wording of independent or not independent. As I said, don't use the word dependent because we are inviting questions that we cannot answer. So dependent, you say. So to what extent, right? Dependent on what? How strongly is the dependence, right? So we are unable to answer all those questions. All that the test can conclude is that they're not independent. So if you like to find out more, you probably have to do a lot more hard work to find out the extent, degree, and manner of dependence, right? So, yeah. Anyway, so we are in this situation now. So we have the hypothesis, and we are going to capture the samples. So we set out to perform measurements, right? So in this case, probably interview. So we ask a lot of questions. Of course, one of the question is, are you from NTU or are you from another university? Uh, then all the measurements, right? So how many interviews have you gone through? What's your initial salary? What's your salary now after 3 years and all that? So we ask all these numbers to combine them to feed into our formula to put them under success, failure, right? So we are going to obtain a table, and this table will look something like, say that alpha equals to 0.05, and the table is going to look something like outcome, success, failure, all right? And we'll put them under the counts, right? So A and B. So putting them all in, we get this. Is that okay? All right. So then what we do is we'll calculate the row sums. Where's our row sum? Okay, our row sum is going to be 5 plus 1, 6. 0 plus 5, 5. Then we have the row sum. And if we have row sum, then we have column sums. 5 plus 0, we get 5. 1 plus 5, we get 6. And the total is 11. So that's like our total sample size. So n equals to 11. Okay. Then what happens is that we want to calculate the expected success based on an induced independence distribution in two-dimensional form. Because this is a two-dimensional histogram, right? I hope you can see a bit like this is the x-axis, this is the y-axis, right? And the block rises to 5-story tall, and this is 1-story tall. This is on the ground, no story. And this is 5-story tall, like that. So this is actually a two-dimensional histogram, but we call it the contingency table. They are filled with numbers, the frequency, but with a bit of imagination, this indicates the floor level that a square building built on top of this plot here will rise to 5-story tall. And this is 1-story, 5-story, 0-story. So this is a histogram. And what we want to do is to assume that population of grouping, population of success failure, they are basically independent. So if they're independent, then the counts, right? The count should be expected to be the product of the row sums and column sums divided by the total. Divided by the total. Due to the definition of probabilistic independence, which we'll discuss in the probability lesson. But for now, let's take it that the expected, expected frequency or count, assuming two variables, in this case, the grouping variable and the success failure achieving success variable are independent, is given by the formula expected frequency equal to the row sum times column sum divided by n. total count. So that is going to give us a calculation that would require these numbers, right? So 6 times 5 over 11 to give us, to replace an expected kind of situation. So let's try to do that. So the expected frequency, let's call it E, and not surprisingly, this is O. Now you begin to see why I put independence test in contrast with goodness of fit test. This is O, this is E. Do you know what's going to happen? Yeah, something like that. Okay, so let's finish up our discussion here. So I just quickly repeat success, failure, A and B, right? So A and B. Okay, so if you do that, 6 times 5 divided by 11, you should get 2.7273. Okay, then 3.2727 and 2.2727. I just quickly write that down because the calculation is really very simple in concept. Just very tedious, especially if your labels here, right? All these category labels, there are many of them, right? And then it's just a lot of number crunching and the data analytics involved. Okay, anyway, we have these, and what is needed is going to be tabulation of the O and E. So if we do the calculations, right? So the O, okay, the labels, right? Which is basically success of A, like that. So success of A, the O, the E, and we're going to calculate the relative error, squared error. So success of A, the observed is 5. The success, is it success? Success of B is 1. Then the failure of A is 0. The failure of B is 5. Okay. The expected, well, success of A, 2.7273, success of B, 3.2727, failure of A, 2.2727, 2.727. Now there's 2727 and then 7272. Sorry about the choice of numbers, it just happens that way. Okay, then I will just do the number computation, right? And I won't bother you with all the simple plus minus times divide square stuff. So the answer is 1.8939. And basically at this point, you will find that the steps involved are the same as goodness of fit. So, reverse engineering back, the lesson learned is that actually we are applying goodness of fit to two-dimensional table, two-dimensional distribution. And this is also a histogram, right? Histogram is therefore a distribution. A distribution here in two-dimensional form, right? So if you can imagine this is 5-story tall and all that, then these are fractional story. Think of the lift going up to the 2.7273 floor, right? So these are the floors, right? So the building is 3.27. We expect these buildings of the heights to be built in these plots, the 4 plots here. If the variable here, variable 1, which is the grouping variable having labels A and B, and variable 2, the success variable having labels success and failure. If these two variables are truly independent, we expect the building heights to be at these levels, these number of floors. But are they, right? We observe 5105. So is it just due to random noise that we can ignore those differences, or is it too much to argue that hey, you know what, two-dimensionally, the errors incurred is not that significant, right? So we linearize the two-dimensional histogram into one serial form. Once it becomes like this, and it really doesn't matter whether you say success AB, failure AB, like what we have done, or you say A success failure, B success failure, also no problem. You can swap, mute them, because what we care about is the total sum, right? So not surprisingly then, chi-square here is equal to the sum of all four values, 7.6389. 6389, right? And that would be our test statistic. Um, So it helps if we just remind ourselves here, right? So the chi-square here is the sum of all the k equals to 1 to the number of cells, right? Number of cells. They are like bins, right? If you look at the previous description, they are like bins, except we linearize the cells into serial form, and that then they are like bits, right? So once it comes to this stage, the two tests basically are the same. All right. From there on, the calculation, the conclusion, the critical value, the p-value, they are all the same. So when we reverse back our thinking, it basically means that assuming that two populations are independent, it would have, right, the samples would have induced this form of distribution, and do the samples 2D distributions match this induced independence distribution. So in some sense, I'm kind of calling this the induced independence distribution. 2D distribution somehow. So clearly it is 2D, right? Okay, so we have the number of cells, and then we have O of k minus, I digress a little bit. So coming back here, E of k squared over E of k. Okay, so that's just a reminder, right? Because I think by now you already know what it's going to look like. Okay, next, it's helpful to try to sketch a diagram. So let's draw the diagram, and the diagram looks like what? Same. Chi-square, right? And we need a degree of freedom. So first thing first, just sketch it. And the degree of freedom that we have is going to be, it's good because the degree of freedom formula changes a little bit. It's going to be number of rows minus 1 times number of columns minus 1. That's it. And not surprising, because number of rows, they have to bound to the same total. Then number of columns, the total has to follow this. So something like that. There's a deduction of 1 degree of freedom from the row before multiplication, and the number of columns. So with this, we have 2 minus 1. So our case, our GF is equal to 2 minus 1 times 2 minus 1 equals to 1, which is terribly low. So again, not advisable to carry on with a small sample size like 11, because you have 2 dimensions, right? You have 2 dimensions, but altogether you only have 11. 11 trying to perform calculations like point estimates and one population mean distribution means or whatever test is already considered small. Much as to say that you have to now cover 2 dimensions, right? So very small, not advisable. But I'm just using this simple a small restrictive example to try to illustrate the steps involved so that we understand what's going on a lot more clearly than just running a function in Excel, R, or Python, and then boom, the answer comes out, and we have no idea what to do with it, right? What to pay attention to, and under what context or what distribution or what precaution should we interpret those outcomes. Okay, so at this point, we can of course draw our Google pin. Where's our Google pin? Wait, what is our x chi-square c, right? Chi-square c. Chi-square is never chi, it's chi-square c. Chi-square c, after my check, it is 3.8415, right? Based on 1 degree of freedom. Based on 1 degree of freedom, it is 3.8415. And our Google pin should be 7.6387, 89. Oh, okay. So doesn't matter. I should be drawing somewhere twice, right? But somewhere over here. Okay. So this point is our chi-square value, which is 7.6389. Clearly, it is in the rejection region, right? So rejection region over here. All right. Then what should we do? Well, at this point, I think you already can hear the voice from your mind saying we will reject, right? We will reject. So since p-value equals to, what is our p-value? I get 0. Here, p-value equals to 0.0057 using chi-square distribution. So since p-value is 0.0057 is way less than alpha 0.05, we reject H naught and conclude whatever H1 says in English. H1 says already in English, two populations are not independent. So we will copy that. Conclude that the two populations are not independent, just to emphasize, are not independent. What did I miss? Yes, to qualify the significance level at 5% significance level. All right, that's it. Now, of course, that's the end of the calculation, right, and conclusion. But what do we do? Well, it is not independent, right? So that's the statistical conclusion, which means that it will affect the outcomes. For example, if you haven't done linear regression, just think of it as a tool, as a model. So we have done, let's say we have computed our linear regression model, right? Say we say use this model to predict, patients' reaction to these new cancer drugs. Oh, it will be a very positive response, blah, 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 blah. Until later, some competitor pharmaceutical companies start to examine the data. They say, hey, you're thinking that the amount of alcohol consumption, right, and the patient's cancer progress rate, they are independent. Our study shows that the hypothesis is rejected, or bracket P is equal to 0.0057. So in that case, what happens? If the two variables, alcohol consumption level and the cancer progress rate, if they are part of the variables used in the linear regression as so-called explanatory variables, that means they are trying to explain the effect of the drug, right? Then that assertion, that assumption, which is necessary when you compute the linear regression, will be invalidated, which means it will weaken the conclusion that hey, our new drug is very effective. Right. So right away, once this result is published, the original drug company who advertised that their new cancer drug is very effective, efficient, right? Straight away their share price will drop, right? Because this is a serious study, right? This is statistically driven and by the scientists, pharmacists in the competing drug company. Yeah, so that could vaporize wealth, right? That could cause the stock market, stock price for the original drug company to fall, and so on and so forth. Right? So unless they point out something, unless the original company points out something here. So what is the something here? Oh, you know what? The sample size is very small, so I suspect your conclusion is not reliable. So, of course, one has to react to this kind of counter attack by the competing company, right now. Yeah, so then we say, hey, you know what? Let's look at your study. Hey, there's a zero, here, right? So there is your sample size. Obviously, it's very small, right? Uh, you even have a zero here, right? So then these will be raising doubts to the validity that the conclusion is the two populations, the two variables are not independent, right? They are independent. They are independent, right? But you cannot just say, no, we think that they are independent. So you can point out, right? So the sample size should be large. That's always an important thing, right? So how large should the sample size be? It should make the cell counts, right? Cell counts should be greater than or equal to 1. So here we have a big problem. This is already a near problem, right? But 0 is a big violation that would reduce the integrity of your conclusion. If your conclusion is that they are not independent, right, it may not be correct. If your conclusion is yes, they are independent, don't trust it. So it's like, then why do you conclude, right? So this is already weakening the conclusion, right? Then you want to have at least 80%, more than or 80% percent of cells should have greater or equal to 5 counts. Okay, so in other words, if we have 4, then 80% will be 3.2 cells, right? So the 3 cells or more. So 3 cells or 4 cells, that means all of them. Our cells are not many in the first place. So 3 cells or more should have each cell 5 or more counts. So the second rule here, this is clearly violating the rule, right? So violating the rule doesn't mean immediate failure, but you're violating all the rules, then we have a big problem, right? So if the scientists, pharmacists from the original company of the new drug comes out and say, okay, thank you so much for your study, right? We're very glad that you joined us in this study, but now comes the sword. Here, right? And so then we will have issues with the reliability of the conclusion. Yeah, then we probably cannot trust that. This is good. And after our test using sample size of 50, we find that, hey, actually it is still okay. We did not manage to reject H naught, and we were able to conclude that amount of alcohol intake and the cancer growth rate, they are independent. It's what we have assumed correctly in our original study, right? So you can see all these back and forth. They are very interesting. They are like Clash of the Titans. All very knowledgeable scientists, well respected pharmacies and branded companies. So they don't come out and say, I think, no, you are not a recognized scientist, you are studying at some unknown university. They cannot do that, right? Because that is arguing at a very low level. So how do you win an argument, right? With grace, with data, right? That's through statistics. With a choice of proper tool, and the tool I'm thinking about is the hypothesis test. Your choice of hypothesis test will lead to, of course, finally the p-value and whether to reject H naught or not. Right. So the reliability, the integrity of this conclusion is also very important. So hopefully now you appreciate the usefulness, right, of these two tests that I've given, the goodness of fit test and the independence test. So we can then look forward to a brighter future for your data analytics career. All right, with that, I thank you very much for your attention and see you in the subsequent videos.